Hold a molecule in front of a mirror. The reflection looks different, left becomes right, atoms swap positions, but the energy is the same. Binding affinity is the same. The physical properties don't change just because you looked at it from a different angle. This is symmetry, and it's the most powerful free information in science. Geometric deep learning builds these symmetries directly into neural networks, so they never waste data learning what physics already guarantees. Biology is full of symmetries. A protein folded in a test tube in Boston has the same stability as the identical protein in a test tube in Tokyo. Translation invariance. Rotate the protein 90 degrees and its folding energy doesn't change. Rotation invariance. Together, these form SE3 symmetry, the group of rotations and translations in three-dimensional space. But mirror reflection is different. A left-handed amino acid and its mirror image have different biological activity. Chirality breaks reflection symmetry. The symmetries of the problem tell you which transformations matter and which don't. A function is invariant to a transformation if the output doesn't change when the input is transformed. The energy of a molecule is invariant to rotation. Rotate the coordinates by any angle, and the energy stays the same. A standard neural network doesn't know this. Feed it a molecule at 0 degrees and it predicts energy A. Rotate by 90 degrees and it might predict energy B. The model must learn from data that rotation doesn't change energy, but this is free knowledge from physics. An invariant network guarantees the same output for any rotation, by construction. Equivariance is the more powerful concept. A function is equivariant if the output transforms in the same way as the input. The force on an atom is a vector. Rotate the molecule and the force vectors rotate by the same amount. If I rotate the input by 90 degrees, the predicted force is to rotate by exactly 90 degrees. Formally, f of t of x equals t of f of x. The function and the transformation commute. Equivariance preserves the geometric relationship between input and output. Group theory provides the mathematical framework. A group is a set of transformations that can be composed, reversed, and include the identity. SE3, the special Euclidean group in 3 dimensions, consists of all rotations and translations. E3 adds reflections. The permutation group consists of all orderings of n elements. Atoms in a molecule can be listed in any order. Each symmetry group defines a contract. The network's behavior must be consistent with these transformations. The group is the specification of what symmetry means for your problem. A model without built-in symmetry must learn it from data. To learn that rotation doesn't change energy, it needs examples of the same molecule at many orientations. For a protein with thousands of atoms in March 22, 2026, the rotation group alone has 3 degrees of freedom. 3 continuous parameters worth of redundancy that the model must learn. Data used to learn symmetry is data not used to learn biology. An equivariant network encodes the symmetry in its architecture. It guarantees correct behavior under rotation and translation from a single orientation. This makes equivariant models dramatically more data efficient. Symmetry in biology, translation, rotation, permutation. Invariance, output unchanged by transformation. Equivariance, output transforms consistently with input. Groups formalize the symmetry contract. Building symmetry saves data and guarantees physics. Next, how to actually build equivariant neural networks.